Okay, here is a simple little theorem. Well, it's simple to state and maybe simple to intuitively understand and feel very clearly that it's true, but actually quite difficult to prove. And the proof will use the pigeonhole principle in a kind of a powerful way. So this will give you an opportunity to see how the pigeonhole principle is invoked in situations where I don't know what you would do without it. Take a set. Let this set have 2n elements. Actually, take that back. Take specifically the set of numbers starting with 1 and going up to 2n. So imagine maybe n is 100, and so we have the set of numbers from 1 to 200. 1, 2, 3, 4, 5, 6, all the way up to 200. Okay, great. So what? Imagine now selecting n plus 1 of those objects. I'm just explaining this theorem in simple language. So in other words, take a little bit more, one more than half of the numbers in this even-sized set. Well, if you do that, if you take 101 numbers out of the set of numbers from 1 to 200, then you must have there must be at least 2 numbers that you have chosen such that they have the relationship that one divides the other. Okay, well, that is very interesting. So many things to say. One is you feel kind of that this must be true in a certain sense. Because, well, if we stick to this sort of toy example of 1, 2, 3, all the way up to 200, the theorem is stated more generally up to 2n, but okay, this seems fine. Why is it true that if I choose 101 numbers, no matter how I do that, there'll be 2 numbers which divide each other? Well, one thing you could do is you could just take is there a way you could do it, maybe we can see why 101 numbers are possible by choosing 100 numbers. And I think if you oh, yeah, that's right. You just take the biggest 100. I think that works, right? If you just choose, so the subset, this set I'm not really giving a name at all, but let S be simply 101, 102, all the way up to 200, then, so take the top half of the set. Well then, yeah, it's just the case that if you have these 100 numbers, if that's your subset, then none of them divide each other, and they're all too big. But if you force me to pick one more number, having already put all the numbers from 101 up to 200 in my subset S, if you force me to pick one more number from 1 to 100, then I will certainly pick a number whose double is already in S, and so then the theorem holds that there are a pair of numbers which divide each other. Okay, I would like to say that this is not a proof. This is not a proof of the general theorem that I have given you a particular subset which almost works, and then tell you that by some subsequent choice, then you fail to make the subset. That feels kind of like a proof, and it is maybe in a very, very informal context that might be sufficient to convince people of what's going on. But there is no guarantee that the subset that you pick must contain the numbers from 101 to 200. Even if you believe deep down that your best chance, so to speak, of picking a subset which doesn't have this property is to start with the top half, that doesn't really prove the theorem fully, in my opinion, because how do you know that this is your best chance? Perhaps there's some other more exotic way of choosing the numbers in set S, which somehow does manage to avoid this property that one divides the other. Okay, so any proof of this is going to somehow be very low level in a certain way, because what we need to do is quantify over every single possible way of choosing n plus 1 numbers from a set of 2n numbers. And even in the case where n is 100, there are, I guess, like 200 choose 101 ways of choosing a subset of size 101. And that's a huge number, and we need our proof to be general enough to account for all those possible cases. Okay, so long-winded ramble. Let's start the proof. I know how to do this. I have no idea whether I would have ever come up with this idea on my own. But after much sort of discussion and playing around and sort of imagining, well, okay, we can keep kind of talking about this, right? So, for example, 1 divides every number. So, once again, I'm trying to sort of break it. So sort of take an arbitrary s, and now just sort of think, well, what numbers are allowed to be in this set S? Well, I definitely can't put, if I'm trying to avoid my subset having this property, suppose this property is undesirable for some reason, that there are a pair of numbers such that one divides another, and I try to avoid it. Well, if I'm trying to avoid this property as I'm selecting my subset, then I better not pick 1, because if I pick 1, 1 divides every other number, and so that's not going to work. If I pick 2, then I can't pick any other odd numbers, or even numbers, because 2 divides every even number. And so once 2 is in my subset, if I'm trying to avoid this situation where there's a pair of numbers such that one divides the other, then no other even number can be in my subset S, because once 2 is in there. And you might think, oh, well, we just take all the evens then, or no, sorry, take 2 and all the odds, but of course that doesn't work, because all of the odds includes 1, and 1 can't be there. And that's not even to say 5 and 25, for example, are odd numbers such that 1 divides the other. So that's not going to work. So so 1 is out, 2 is out. What about 3? Well, once again, if I pick 3, then no numbers which are multiples of 3 can be in my set. And so, I don't know, you get this sense that kind of small numbers are bad, so to speak, because if you pick a small number, then no multiple of that number can be in the set. And this is maybe what would have led us to think to take the top half, which is what we were just talking about. All right, so the idea here is that I don't even know how to fluidly transition from this way of thinking to the main idea of the proof. But what we sort of want to do, what's sort of relevant, I guess, to every one of these numbers in my set is we definitely want to consider their prime factorization. For example, when I speculated just a minute ago about including 3, then I see that no number which is a factor of 3 or multiple of 3 can be in there. And so I kind of want to consider every single number and its prime factorization. And one thing, well, I guess I'll just go to it right now then. Although I do think the insight I haven't explained yet. Maybe it will come to me. Yeah, what I want to do is factor every number into its sort of even component and its odd component. There is surely a term for this, and I just don't know it. But you can take any number, like, I don't know, 150 or whatever, and split it up into, what is 150? It's like 6 times 25. And so this, in fact, turns out to be just 2 times 75. And so this number is the power of 2, and then this number is necessarily odd. Take some other number, maybe more exciting, like 96. What's 96? It's like something big. It's like 16 to 32 times 3, I guess it is, right? Yeah, it's 32 times 3. So this is 2 to the 5th times 3. And okay, if you give me another number, oh, I don't know, 48. Well, 48 is 16 times 3. And so now this is 2 to the 4th times 3. And so we sort of think of every number as, well, can be factored, of course, according to the fundamental theorem of arithmetic. And let's factor it into sort of two numbers, one being a power of 2 and one being everything else. Well, what's nice is that the everything else, so here's power of 2, power of 2, and then this is odd. And as you see, if you take 48 and 96, well, then they can't both be in set S if you're trying to avoid this property, because 48 divides 96. And in fact, if any two numbers have the same odd number left over, then that's a problem. Because they must divide, the smaller one will then divide the bigger one. Okay, and however, there are only n odd numbers possible from this set, and therefore it's not going to work. Okay, let's now just do the proof. This is not really such a good video, I am seeing now. Okay, so here we go. By the fundamental theorem of arithmetic, each of the elements in this subset S can be factored in this way. It can be written as just factored into a product of primes. That's what the fundamental theorem of arithmetic says. It can be expressed as some power of 2 times some other number. And okay, what is k? So where k sub I is some number greater than or equals 0. It's just the integer power of 2, just the number of 2's that appear in the prime factorization of this element. And of course, if you factor out all the powers of 2, then what's left over is going to be the remainder of I don't want to use the word remainder, it's the rest of the prime factors. And since 2 is the only even prime, all of the remaining prime factors will be odd, and the product of all of those odd primes will also be odd. So Qi is odd. Okay, and yeah. And now, okay, this is almost doesn't need to be mentioned, but since this number Qi divides Si, then that means that Qi is less than or equal to, I guess. It says less than on my packet, but of course, if the element S sub I is itself odd, then there will be no there'll be no 2's in the prime factorization. So k sub I will be 0. So it's possible that q sub I just is S sub I if S sub I is odd. But okay, so q sub I is lesser than equal to. So why am I mentioning this? That since S sub I is by definition an element of 1, 2, 3 all the way up to 2n. Then so will q sub I be an element of 1, 2, 3 to 2n. Okay, and yet, but, and here's the catch, but as I said, there are only n odds in this set 1, 2, 3 all the way up to 2n. And so what we are now going to do is think of the odd numbers as the pigeonholes, so to speak, and think of the n plus 1 numbers in set S as being the pigeons. And the pigeonhole principle says that, if you have n plus 1 numbers in this subset S, and you have only n odds all the way up to 2n, then there must be, so I'll just say this right now, I guess I'll just write this, since we have n plus 1, this is what I was just saying, since we have n plus 1 elements in S, and, maybe this is the more organized way of putting it, and hence we have n plus 1 q sub i's, right? Because let q sub I be, the odd, the product of all of the odd prime factors for each of the elements of S. We have actually n plus 1 of them, but only n possible odds there are only n possible numbers that can be q sub i's, I guess is the way of putting it. Then by the pigeonhole principle, two elements of S must have the same q sub I. Let's call them A and B, call them A and B. And so what it means, the pigeonhole principle says that no matter how you try to do this, you're going to end up with one of your numbers in your subset being of the form 2 to the k times q, and you're going to have another number b of the form 2 to the j times q. And in other words, factoring out all of the evens, or expressing the number as a power of 2 times the product of all of the odd primes, you're guaranteed to have two numbers that look like this, where for those two numbers the product of all the odd primes is the same. And that just has to be because there are only n different possible values for q, and yet you've chosen n plus 1 numbers. This is the heart of the proof right here. And so now we're basically done, because if you give me two numbers of this form, then just like the 48 and the 96, one of them must divide the other. And so if j is less than or equal to k, then this one is smaller. I don't know why I said less than or equal to, because I guess these just have to be different numbers. So this really should be less than. If j is less than k, equal to is not an option. If j is less than k, then b divides a. And if, on the other hand, k is less than j, then a divides b. And so you're guaranteed to have two numbers, one of which divides the other, and that was what we wanted to show. Okay, woo! Extremely inefficient video. Goodbye!